Welcome back. So, this is lecture number 21 and here we are going to talk about hysteresis control method in switch mode power converter. So, in this lecture we are first going to discuss state dependent switching and limit, voltage hysteresis control and stability, then current hysteresis control and stability and implementation method for hysteresis control and steady state analysis. Of course, there will be MATLAB simulation also. So, if we take the phase plane behavior of a buck converter, the synchronous buck converter, and this shows the trajectory where if we set, let us say t equal to 1 microsecond and we turn on the switch for t by 2 and turn off for t by 2, then how can we generate Q because get signal? That means, here if we take just simply 50% on and 50% off, that is very simple. It is like an open loop converter, there is no control. But if we want to replicate this waveform which is shown here, if we want to replicate this waveform in the phase plane where this is the output voltage and this is the inductor current, then how can we generate the switching signal Q, and can we do it purely based on voltage based control? Okay. So, can we implement based on voltage based switching surface, voltage based switching surface? So, here we are talking about again the phase plane where x axis is the output voltage and y axis is the inductor current. And if we take this line, this line actually corresponding to this line corresponding to a vertical line where we want to achieve the desired output voltage, reference voltage. Now, if we take an initial condition here, the simplest logic can be if any condition like if the state, the voltage is smaller than Vref, then you should turn on the switch, and if the voltage is higher than Vref, then you should turn off the switch. That means, once it is attracted towards Vref and it crosses, you see the multiple thing. That means, we need like a turn on and off logic based on whether the voltage is left side or right side, and this require infinitely fast switching action, and that is like something called chattering action. But this impractical switching action is not practically possible, and in fact such fast turn on and off can damage the MOSFET. Then what to do? So, we need to incorporate some kind of hysteresis band, and if you see the waveform, we want to achieve Vref, which is let us say average is the Vref, the middle portion, and we can set a higher VH which is Vref plus delta VH by 2 and VL which is Vref minus delta VH by 2, where this delta VH is my hysteresis band, this is my band, hysteresis band. Okay. Now, the output voltage ripple in a DC-DC converter or a buck converter, it is dominated by ESR. So, we need to take a little larger ESR in order to capture this ripple information correctly. And also in buck converter, it can be shown if the ripple is little bit larger, that means that if the ripple of the output voltage due to ESR is dominant over the ripple due to the capacitor, then the voltage ripple will be in phase with the current ripple. Okay, and then the slope of this voltage ripple, rising slope of this voltage ripple is same as that. That means, if we take the rising is MV1 is nothing but ESR into the rising slope of the inductor current. Same thing for the falling slope. Then we can compute the on time and off time from this waveform by substituting the slope information and of course, the hysteresis band. Then we can compute, okay, this is what I told RC into M1, same thing for MV2 also, that means MV2 is also RC into M2. Then we can compute the total time period, and which for a buck converter, if you substitute M1 and M2, the rising and falling slope of the inductor current, then we can get the total time period, which is a function of hysteresis band, ESR, inductance, then input output voltage combination. That means, for a given input output voltage, this switching period is directly proportional to delta VH if all other parameter, let us say ESR is more or less constant, inductor is constant, and input voltage output voltage are constant. But it is not so simple, because input voltage can also vary, then you can have a variation in the switching frequency. Also, the inductance, which actually if you take the Bage characteristic of the inductance, so that nonlinear characteristics of the inductance can also affect the time period drastically. That means, it is sensitive to many parameters. Okay? So, it is sensitive to ESR, it is sensitive to the nonlinear characteristics of the inductor, nonlinear BH characteristics. It is also sensitive to this, the hysteresis band, of course. So, switching frequency is sensitive to input voltage variation, ESR variation, inductance variation. Switching frequency can be programmed by adjusting delta VH, and frequency regulation require a separate frequency loop. Now, so we talked about hysteresis comparator. I just want to briefly touch upon, using an op amp you can actually implement a hysteresis comparator. So, if you take an op amp like in open loop, it has a positive supply rail and negative supply rail, and this is a inverting like a negative terminal and the positive terminal of the op amp. It is in open loop and A is the open loop gain. Okay, so all these terminals are defined, positive negative supply rail and open loop gain of the op amp. So, if we take the transfer characteristic of the op amp, that means the input output characteristics, if we set the negative voltage to 0 and the positive voltage to V in, then what we will get? The op amp will be linear in the linear region as long as the voltage, output voltage of the op amp is within the supply rail, Okay? That means, this is the transfer characteristics. Now, this region of input voltage of the op amp and the slope, particularly this slope, it depends on, so we decide that in the linear region output voltage is A into Vp minus Vn. Okay? That means, if you take this Vp minus Vn, which is the decided by the input voltage in this case, even for the same range, even for the same input voltage range, if a op amp has a very high open loop gain, then this slope will be almost, this slope can be increased. That means, we can increase this slope by increasing the open loop gain of the op amp. That means, if the input gain is infinitely large, then the op amp characteristic can be approximated as a pure comparator. Okay? So, linear range is almost region neglected and op amp will act like a pure comparator. Now, in this condition, that means, we are talking about very high open loop gain when the op amp will essentially work like a comparator in the open loop. If we take Vn equal to Vref, that means, if we take the negative terminal as a Vref, then we can shift the transfer characteristic, that range can be shifted. That means, if your input voltage is higher than Vref, then it will be on high supply rail, if it is lower, it will be lower supply rail. Okay, so, if Vp equal to Vref and Vn equal to then we can shift. So, that means, we can change the transfer characteristic based on what supply you are considering at the two terminals of the op amps. Now, if we add a positive feedback, that means R1, R2 and this source series resistance, then it actually acts like an inverting Smith trigger circuit, and that we have learned in analog circuit, and under this condition, if we keep on deriving the output voltage expression of the op amp, then it turns out to be the output voltage of the op amp will take this form. That means, whenever it is like a hysteresis band, okay, this hysteresis band, and this is the return path of the band. That means, if Vin is less than, that means if Vin is less than this VL dash, then the output will be high, and if Vin is greater than this, the output will be low. Now, if we take a non-inverting configuration, then we can, in non-inverting configuration, then you can get the hysteresis comparator like this. I mean, these are standard implementation of hysteresis comparator, and this can be available in any standard analog circuit book. But what we are interested in, how to implement, that means this technique can be incorporated into an op amp, so that op amp can be configured as a hysteresis comparator. Now, in hysteresis current control, in terms of integrated circuit, in fact, this is the sense voltage which corresponds to the sense inductor current, and we talked about the sense inductor current. If you take a resistive sensor, that means, if we want to put the, that means I am talking about the inductor. If you take a direct sense resistance of the inductor, and if you put a current sense amplifier, the current sense amplifier, then I talked about that the VSN, and this is your IL. So, VSN will be some R equivalent into IL, where R equivalent include the sense resistance multiplied by current sense amplifier gain. There are other technique of current sensing like a DCR sensing, where you do not need to put a physical resistance, but if you put a parallel, that means suppose if this is the DCR of the inductor, if this is the inductor DCR, and if you put a capacitor and a resistance in parallel, then by sensing this capacitor voltage and matching the time constant, you can get nearly the same waveform of the profile of the inductor current. But in all cases, these are sense voltage which corresponds to the current, and we can set, we have discussed about the Smith trigger or a hysteretic comparator, and we can set accordingly the hysteresis band. This is my hysteresis band. What is my hysteresis band? Okay, yeah, this is the hysteresis band. We can set it. Next, if we set the hysteresis band and if you go by the sense current base approach, then what would be my switching frequency? Since it is a sense inductor current, that means in generally M1 is the rising slope of the inductor current and M2 is the falling slope of the inductor current. And here MS1, MS2 means M1 into sense equivalent sense resistance, we have to multiply. So, this is the equivalent sense resistance. Okay. So, you can multiply, we can MS2, then we can compute the on time, and this is a voltage hysteresis band which corresponds to analogous current hysteresis, because we are taking the sense inductor current which is a voltage. So, you can compute on time, off time, then we can obtain the total time period, and from there we can find out that switching frequency expression in terms of sense equivalent sense resistance, the current hysteresis band which is represented by equivalent voltage hysteresis, and then the slopes. And if we substitute, then we can find, and we will do it. Okay, here we are going to represent, we want to implement the hysteresis current control in MATLAB. Okay. So, in MATLAB we are not going to use a circuit implementation of Smith trigger and other stuff. We want to implement a simple logic of hysteresis current control. Before we move forward, we want to show the waveform of the current. Okay. So, here we are going to consider this is one band and this is the other band. Okay. So, this is my higher band and this is my lower band. Okay. And my inductor current, we want to ensure the inductor current should be within this band. This is my inductor current. So, this is a inductor current implementation. Okay. That means our logic should be such that, so what is my logic requirement? Logic is that if IL is less than equal to IL, then Q goes high. If IL is greater than equal to IH, Q goes low. Else Q retains its previous state. Okay. Else Q retains its previous state. Okay. Now, I want to implement this logic. How can I take? I take two comparator, one here, the other here. Okay. These two are the ideal comparator, no hysteresis comparator, because in MATLAB we just want to use a logical comparator which looks like an ideal comparator, and we want to use an RS flip flop, that is R, S and Q. Okay. Here we want to consider this is my current. So, this is my current feedback, inductor current. See, in order to turn on this switch, we know this logic should be set. So, this should be my IL and this should be my IH. And what the logic says, this logic, if IL goes below IL, that means if this quantity become high, this is low. And what this logic says, if IL goes above, this is plus, this is minus. So, this represents our implementation, and what is this band? So, this is my hysteresis band. Now, I am going to show a MATLAB simulation where I want to implement a buck converter where I want to introduce two loop. That means, first I want to show a purely current hysteresis band. Okay, let us go to the MATLAB implementation. Here I am showing a current hysteresis control. Let us say I want to keep the current. So, let us see what is the load current. So, if my load current, let us say is 20 ampere is my load current. So, I want to maintain between, I want to put a 4 ampere hysteresis band. If my upper limit is, that means what is my design objective? Let us say my objective my I load current is 20 ampere, that is given, that means I want to achieve, that is given. So, IH should be and delta IH, let us say I set it like a 4 ampere, then IH should be 20 plus delta IH by 2, which is 22, and IL should be 20 minus delta IH by 2, which is 18. Okay. Now let us see whether can we implement in MATLAB or not. Okay. So this is one logic. This is going to reset. So this should be the peak. This should be the valley. Okay. So this is the valley where we are going to subtract. All right. Okay. So in both these cases, we want to, so we took already the comparator and 20 ampere is my limit. That means 20 ampere is my current ref, high ref. So this is my 20 ampere. Okay. So this is 20 ampere, this is also 20 ampere. What do we want to add? I want to add delta I H by 2. I will recall that delta H by 2 I want to add here, and here the same thing I want to subtract. That means one we are adding and another we are subtracting. Okay. Now let us go back and we will set 20 ampere current. Okay. So I ref, that means this is my 20 ampere. Okay. And what we took here is the delta IL. So we will copy paste here, let us say 4 ampere. Okay. So here we are not using any closed loop control. So we can simply disable this block and let us run and see what happens. Oh, okay, because it is there in the loop. So we want to see that can we get, okay. So you can say in this waveform that we are getting like a, it is current is varying between 18 ampere to 22 ampere, 18 ampere to 22 ampere, and my average is 20. It is perfect, but there is no regulation in the voltage because we left the voltage open, though we have applied 20 ampere load current, but because due to the drop, the balance, average inductor current, if we set 20 ampere and if we expect the average voltage to be, because the same average current is going out as a load. So the voltage depends on the charge balance in the overall cycle balance. So that is why we do not have any control over the voltage, but we can add the closed voltage loop. Okay. Now if we want to regulate the output voltage at the same time, so what modification we want to do? Now the peak reference, that means this 20 ampere which is a reference, that I will take it from the closed loop. That reference I will take it from the closed loop because that is the reference. Now the other things are all same, that means I will tell you what exactly I am doing. Okay, running for let us say 2 millisecond. Okay, here what I am doing, earlier we said, now you see we are getting few things we need to observe. The first thing, though we are now getting close to the regulated voltage, that means 1 volt is nearly coming to the 1 volt, but we set 4 ampere voltage threshold limit. That means if we check this 12.21.5 and 18.5, close to that, but it is coming only 3. That means though I initially when we set, what I am comparing, let us hold it, I will just hold this value. The one case we are closing the outer loop and another case we are not closing the outer loop. Okay. And what we are doing here, we again open the outer loop and what we set was 20 ampere is a reference. that we will set it here. So, one case we are using a fixed reference, and C I want to show what actually happened. So, two things we can see here, we can notice here. The first thing we will notice that when it was running under open loop, and if we grid it, the current is perfectly maintained between 18 to 22, that was our desired value. That means, we want a 4 ampere current ripple and the average should be 20, everything is fine, but the voltage was not regulated. But if we want to regulate the output voltage, we close the loop, then we found the voltage is getting regulated here, that means it is getting regulated here, it is getting regulated here, the red one, but the current is no longer 4 ampere, though we set 4 ampere hysteresis band, but is no, that means there is something which is causing some actual inductor current ripple is not exactly the same as the desired one. And there are research paper which shows that this is due to the output voltage ripple effect. Now, if we make the ESR to be 0, I will show you under the closed loop. Now, we are doing closed loop and I am using a green color. Again, I am using closed loop, okay, and let us go, and I am breaking this loop and using closed loop. That means, I am just moving it. Now, it is closed loop, but we are making some changes in the power parameter, where we are considering ESR to be 0, and I want to show you what happened if we run this simulation. Now, it is under closed loop, okay. Now, we want to see what happened. Great. Now, you will see very interestingly that if we take, particularly let us say this point, now the green color is almost achieving 4 ampere current ripple. That means, the inductor current ripple is more or less same as the hysteresis band, and also the output voltage is getting regulated for the green waveform. That means, there are three things. The first thing, the blue one is the current loop open, outer loop open, only current loop close. That means, we are setting, but there was no regulation in the output voltage, that we found. That means, I am just comparing 3, and if I take the final few cycle, that means close to 2, I am just taking final few cycles, that means here. So, what are the observations? That means, the first one is the green one, where it is under open loop and we are making sure the current track perfectly between 18 to 22 ampere, and that is exactly happening, but there is no regulation in the output voltage. Second, we now we close the loop, and this is a red color, though we set 4 ampere hysteresis band, but we are not achieving, we are getting less. And the third case is the green color, where we remove the ESR and it is under closed loop and we are getting close to. That means, the hysteresis control, if we close the loop, that ripple has a direct impact on the actual current ripple and the hysteresis band, and this have been well reported in the literature. It is sensitive. So, but in general, in buck converter, the switching frequency is proportional, inversely proportional to the hysteresis magnitude, and also depends on the sense resistance and so on. So, the parasitic effect of hysteresis control, if we take purely voltage hysteresis control, then if there is any parasitic ESL, effective series inductance, that can introduce some jump and that can cause some problem in hysteresis control. So, you have to be very careful in terms of layout and other stuff if you want to go directly by voltage based hysteresis control, output voltage. So, that means we have discussed the basic of hysteresis control, we discussed voltage and current based hysteresis control and implementation, MATLAB simulation also we have shown, op amp based hysteresis comparator design we have shown, and advantage of limitation of hysteresis control are also discussed. So, with this I would like to conclude this session. Thank you very much.